Hello and welcome again to the Academy. This is a video, part of a video series on Cal 3 topics, and this time I'm going to be talking about the gradient theorem. Sort of a continuation of the previous video on line integrals, where I was talking about, in particular, one type where you have a vector field f, and you can take the integral f.dr to find, for example, the work if f represents the force. And I want to talk about a special case of this. And the special case is, what if f is a gradient field? Basically, the gradient of some function f. F is continuous and differentiable because, well, the gradient is the partial derivatives. So it has to be differentiable for the gradient to exist. And so this is, well, the integral then becomes gradient.dr. And what I'm going to claim here, let's say your path C goes from a point P naught to point P1. Then what I'm going to say is, what I claim the theorem is, here's the theorem, that this is simply f of P1 minus f of P naught. Or in other words, that it only depends on the endpoints P1 and P naught, and it doesn't matter what path you take to go there. So let's see why this is true. Show a little proof here. So, now let's think about the two-dimensional case first, but it works in 3 dimensions in any number of dimensions you want. Let's go about how to evaluate this. So, if f is a function of x and y, then the gradient of f, as we know, is going to be the partial derivatives. So the vector of the partial derivatives with respect to x, and the partial derivative with respect to y. And so again, we have to talk about what our path is. Here's our path C. C, we're going to have x be a function of t, and y also be a function of t. I don't know what c is, and I've claimed that any arbitrary c will give you the same results as long as t goes from, let's say, a to b, where t of a, or when t equals a, you're going to have p not your initial point, and p1 is going to be where it's going to correspond to when t equals b. So it goes from a to b, and so your point, the x and y coordinates, go from the p naught to p1. And so this, again, we have our r is just x and y, and dr will just be the derivatives . So now we can substitute this and put everything in terms of t. So now t will go directly from a to b. And so this is going to be partial derivatives dot product with what's dr, which is the derivative x with respect to t, dx over dt, and dy over dt. And then all with dt at the end. And so now we take the dot product, integral from a to b, of multiply the x components, we get partial f with respect to x times dx dt plus partial of f with respect to y times dy dt dt. So now if we look at this, this may look slightly familiar. It's actually the chain rule talked about in a previous video. The multivariable chain rule, which I said that, just sign over here, chain rule. So it goes both ways, of course. This is the same as this. So that we can simplify this. In fact, we integral from a to b, well, this is just going to be df dt dt. So it's just the total derivative of f with respect to t. And so the integral of the derivative, this is going to be the original function f of t in this case. Because now f has become a function of t because we substituted x and y as functions of t from a to b. So it's f of b minus f of a. But as we said earlier, b and a are really the beginning and end points of our path. So the point P0 is when t equals a, and the point P1 is when t equals b. This is really f of P1 minus f of P0, which is what we said here. So there's the proof of that. And so, what are the implications of this theorem? Well, one of the things I have is path independence. Which says that the integrals of these functions, these vector fields that are also gradient fields, are path independent, which means that it doesn't matter which path I take, to get from our first point to the second point, the integral will be the same. It just depends on the end points and not on how you get there. And so, just as an example, let's do one where we do a couple of different paths and show that they are equivalent. And they are in fact equivalent to this. So let's use, let's say f of x, y is xy minus x cubed, for example. So the gradient is going to be the partial derivative with respect to x is going to be y minus 3x squared. The other one will be with respect to y, so it's constant, so x. So let's say we want to integrate from this point 0, 0 to the point 1, 1. we can go in a straight line, or we can go various other ways. We can go like this, a parabola, where we have y equals x squared, for example. So this is two completely different paths, but since this field is a gradient field, they should give the same result according to the theorem. So let's actually do it. So let's call this C1, and this is C2. So the integral of C1 over C1 of f dot dr, well, C1 is going to be x equals t, y equals t, is the simplest way of doing it, where t goes from 0 to 1. And this is f, so if x and y are both t, this becomes t, in this case f is going to be t minus 3t squared, comma t. So this integral will be 0 to 1 of, I forgot dr will just be the derivative of this, so it should be 1 to 1 dt, t minus 3t squared, t, I've got 1 to 1 dt, which is the integral from 0 to 1 of, that's going to be plus t is 2t minus 3t squared, integrating integral of 2t is t squared, and integral of 3t squared is t cubed, which is going to be 1 minus 1, it's actually just 0 in this case. Strange enough. Well, let's do C2, maybe we'll get a different result. So integral over C2 f dot dr. Now we're going to have C2 be x equals t, y equals t squared. Again, from 0 to 1. Our r is t comma t squared. So dr is just 1, 2t dt. And f becomes, well, xy is going to be t times t squared, which is t cubed. Wait, no, what I'm saying. F is this. It's going to be t minus 3t squared. T squared minus 3t squared. Which is just going to be comma t. So that's just negative 2t squared, comma t. So the integral becomes, integral from 0 to 1, negative 2t squared t, 1 comma 2t dt, negative 2t squared plus 2t squared dt. And where now? Integral from 0 to 1 of 0. Integral of 0 is 0. And so it's also 0. And finally, let's do it another way. If we knew that it was the gradient of this original function f, then we should just be able to evaluate f at this point and subtract it from f at that point. F at p1 minus f at p0. So p1 is just 1 comma 1. And so when we put 1 here, we just get 1 minus 1, which is 0, minus, when we put in 0 comma 0, we just get 0 again. 0 minus 0 equals 0. So all methods worked, because of course the theorem is correct. Let's prove it right here. talk a little bit about how this theorem is kind of a generalization of the fundamental theorem of calculus. Now, if you remember this one, it just states that the integral of the derivative will just give you the original function evaluated at the endpoints, or you subtract the function at the endpoints. Or in other words, draw a picture. The integral of this function is the integral of, let's say this is the derivative of a function, will just be the function evaluated at b minus the function at a. And similarly, this is a more general form. This talks about the integral of the gradient, which is kind of like a derivative. It's a form of derivative for vectors, or it's a derivative for multivariable functions. X and y, or more than one variable. And then if we integrate this WR over any path that goes from initial point to the end point, once again we get the same thing. We just get f at the boundary of our curve. In this case, the boundary of this interval. The boundary of the interval is just the endpoints. And in this case, against the endpoints. But the interval, or in this case our curve, can be anything. But it's a generalization to the more general form that says that the integral of this derivative form will just give you, reduces to just the boundary or the endpoints. F of P. So now I want to talk about an interesting corollary of this theorem. And that is, if we consider that C is a closed curve. Say it starts at this, and let's just call this point, this big point here. Now the integral over a closed curve of a gradient field, and if you see the closed curve, a lot of times we draw a little loop here in the integral to show that it's a closed curve. Well, since we know there's going to be the difference at the endpoints, well, what is the endpoint? We pick this point to be the starting point. It is also the endpoint because it's a closed curve. So it's just f of p naught minus a p naught. So it's always going to equal 0. And a lot of times functions or fields, vector fields that are gradient fields, also called conservative vector fields, because this integral equals 0. So the work done in a closed loop is 0. So if this is f and this is the work, which means that energy is conserved. And so if it's a gradient field, then it conserves energy. So you can't actually get energy by moving it in a straight line. If you move it back to where you were before, you'll just be at the same energy. And fields like this include the gravitational field. We're going to have to take this point here and then move it around, and it comes back here. It has the same potential energy. Sometimes this function is called the potential. So it still has the same potential energy, so I didn't actually create any work. There was no work done by the field. So it's called conservative because it conserves energy. Now I just want to do one more example of functions, or of vector fields that are not gradient of a function, but are not conservative. Let's consider this vector field. Negative y comma x. And we did this one as an example earlier. It looks something like this. Counterclockwise rotation. And so what if we wanted to find the line integral of a counterclockwise circle, let's say the unit circle. Let's say this is C. If this were a potential or a gradient field, if it was the gradient of a potential function, then it should be equal to 0 according to this corollary of the theorem. So let's see. Our curve C. Well, we can just say x equals cosine t, y equals sine t from 0 to 2 pi. And r cosine t, sine t, dr is negative sine t, cosine t dt. And f is negative sine t, cosine t. So the work done, or the line integral here, f dot dr, integral from 0 to 2 pi of, well, it's going to be negative sine t, cosine t, dot product with negative sine t, cosine t dt, which is 0 to 2 pi. Negative sine t times negative sine t is going to be sine squared t, plus cosine squared t, t, and we know sine squared plus cosine squared is 1. So just the integral of dt, which is 2 pi, which is not 0. And so we've shown that it is not a conservative vector field. F is not conservative. And therefore, there is no function f such that the gradient of f will give you this vector field. So there's no function whose gradient is this field right here, because if it were, then this integral, this happens to be a closed loop, it would have been equal to 0, but it's actually equal to 2 pi, so the work done is positive, even though we went in a circle. And there are some fields in nature that are not conservative, like magnetic fields. They're not conservative because they do curl around in a circle like this. And so, yeah, that's all for the gradient theorem. Thanks for watching, and I'll see you in the next video.